Today's session is going to be a continuation to the previous part, as we are going to wrap up the introduction to error analysis by going over the propagation of error and the linear regression. Starting with the propagation of error. In the previous session, I gave you a very brief and general overview regarding the propagation of error. Basically, I said that in that case, we are going to have a main parameter, and that main parameter we are going to label it as a main function. And that function, it can be a function that depends on one or more than one variable. So it can be a function of x, for example, f of x, or it can be a function of two variables, therefore a function of x and y, or it can be a function of three different variables, x, y, and z, or it can be a function of multiple amount of variables. Now when we say that we have a function of a certain variable, what do we actually mean by the term variable? The term variable in that case implies that the physical quantity which we are referring to as a variable, it has an associated uncertainty. Therefore, it is no longer considered a constant, but rather a variable. For example, x, it can have an associated uncertainty, delta x, therefore it becomes a variable. The same thing for x and y, and the same principle for x, y, and z. Now let's consider the following function, f of x, y, and z. And let's assume that each of these following physical quantities, x, y, and z, they were actually measured in the lab. Therefore, they are going to have associated uncertainties to their values. So on x, we are going to have, let's say, an associated error alpha x. On y, we are going to have an associated error alpha y. And on z, we are going to have an associated error alpha z. In that case, f is going to be a function of three different variables, x, y, and z. Moreover, if these uncertainties over here, they are actually random and independent. Independent meaning that the error on y, it was not determined by using the error on x, and the error on z was not determined by using the error on y, etc. So they are independent values. They are independent from each other. Moreover, if these errors are actually random in nature, they are random errors. Therefore, in order to find the error on that main function f, we are going to be deriving f 3 times with respect to each one of its variables. So the equation for the error is going to consist of partial derivatives of f, once with respect to the first variable x, another time the derivative of f with respect to y, and the third time the derivative of f with respect to z. So mathematically, the equation is going to be given as following. So the error on f, the error on that main function f, is going to be given as the derivative of that main function f with respect to its first variable x multiplied by the error on x squared plus the derivative of the main function f with respect to its second variable y multiplied by the error on y squared plus the derivative of f with respect to z times the error on z squared. And then we take the square root of that entire equation. And that would be actually the general equation for the propagation of error, which, as we can see over here, it consists of a series of partial derivatives of that main function with respect to each one of its variables. And each time we multiply that partial derivative by the error. Now, of course, you might be wondering, how did we actually get to that final form for the propagation of error, and what is actually the critical thinking that led us to use partial derivatives and multiply them each time by the corresponding error in order to establish that final form for the propagation of error. In order to answer these questions, we are going to work our way up bit by bit by considering special cases for the propagation of error, and then later on we are going to be generalizing these cases in order to form that general equation, that final form for the propagation of error. We are going to begin with the first example for the propagation of error. We are going to consider that we have two cylindrical rods of two different lengths. And we are going to consider that the length of each rod was actually measured in the lab. Therefore, we have an associated uncertainty estimate or an associated error for each length. So for example, let's say L1 is actually equal to 30 centimeters plus minus a certain uncertainty estimate of 0.3 centimeters. So that fraction over here, it corresponds to an uncertainty estimate, or simply you can consider it a margin of error on that value of length. And L2, let's say it's equal to 40 centimeters plus minus a certain uncertainty estimate of 0.4 centimeters. So these are random values, random errors. And that value over here also it corresponds to an uncertainty estimate. Now, let's say that you put some thin layer of glue on one end of that rod and you connect both rods together in order to form one single rod. So over here, let's say now we have the following new rod which consists of the previous two rods. And the target in that case would be to find the entire length of that new rod in addition to finding the uncertainty estimate on that length. So over here I'm going to refer to the uncertainty estimate as delta L. We have seen before that the error actually we refer to it as alpha. Now I'm going to be using a different notation. It is actually similar in terms of the definition, but in terms of notations or in terms of symbol it actually differs. So I'm going to be using delta L to refer to that uncertainty estimate or to that error. Now in order to find the length of that new rod, we are going to consider actually the best estimate of L1 and L2, meaning we are going to consider the expected values of L1 and L2 without factoring in the amount of uncertainties on each of L1 and L2. So in that case, the entire length of the new rod will be L1 plus L2, which is equal to 30 centimeters plus 40 centimeters, which is equal to 70 centimeters. And that would be called the best estimate, or simply the expected value of the length of that new rod, which consists of the length of L1 and L2 without factoring in the amount of uncertainties on each of L1 and L2. Now after determining that expected value for the length of the new rod, now we need to determine, like I said before, the amount of uncertainty on that length, or the error on that length. How can we determine it in that case? Now to answer that question, we are going to follow a numerical approach. We are going to look at the maximum and minimum values of L1 and L2 when factoring in the uncertainties on them. Meaning that over here L1 it has a certain error on it. So if we add that error to that value of the length, therefore you would be finding L1 max. And if you subtract that value from the length, you would be finding L1 minimum. And the same thing over here. If you add that amount of uncertainty to 40, therefore you would be finding L2 max. And if you subtract that value from 40, you would be finding L2 minimum. So in that case, we are going to be finding over here L max and L minimum, which both correspond to adding or subtracting the uncertainties from L1 and L2. So let's start by finding L max, which is equal to L1 max plus L2 max, which is equal to, so L1 max is what? L1 max is 30 centimeters plus 0.3, which is 30.3 centimeters, plus L2 max, which is 40 plus 0.4, which is 40.4 centimeters. So the total would be equal to 70.7 centimeters. And that value over here that we have obtained, we are going to refer to it as the overestimating of L max, or the overestimating of the length L. So that value over here is actually the overestimate of the length L. Why do we call it the overestimate? Because simply we are adding each uncertainty estimate to the initial length. Now in a similar manner, we are going to be finding L minimum, which is equal to L1 minimum plus L2 minimum. L1 minimum is what? L1 minimum would be 30 minus the uncertainty estimate. So it is actually 29.7 centimeters plus L2 minimum, which is 40 minus 0.4, which is none other but 39.6 centimeters. Therefore, the total would be equal to 69.3 centimeters. And in that case, we are going to consider that result to be now the underestimate of the length L. So that result over here, we are going to refer to it as the underestimate of the length L. So as we have seen over here, we have established three different values for the length. We have L expected, which is found without factoring in the errors on L1 and L2. We have the overestimate value of L max, or simply L max, which consists of adding each uncertainty estimate on L1 and L2. And then we have the underestimate value of the length, or simply L minimum, which is found by subtracting each error from each length, from L1 and L2. Now if we look over here, that value of 70 centimeters, the expected value, it actually lies right in the middle between these two values, between the 70.7 and between the 69.3. So in that case, we can be sure that our expected value for the length is actually equal to 70 centimeters. However, that expected value, it actually deviates by 0.7 centimeter from L max, and it also deviates by 0.7 centimeters from L minimum. So that actually implies that the amount of deviation, which is none other but the uncertainty estimate, is actually delta L equal to 0.7 centimeters. So the uncertainty estimate and L expected is none other but delta L equal to 0.7 centimeters. Moreover, how can we compare that value of delta L equal to 0.7 centimeters to delta L1 over here and to delta L2 over there? As we can see, delta L1 is equal to 0.3 and delta L2 is actually equal to 0.4. So delta L1 plus delta L2 is actually equal to 0.7 centimeters. So that implies that delta L is actually equal to the uncertainty estimate on L1 plus the uncertainty estimate on L2. And that would be the final result that we are actually aiming for, which actually states that whenever you have two measurements and on each measurement you have an error, therefore by summing up these measurements, by adding them up together and forming a third quantity, therefore the error on that third quantity is going to be none other but the addition of the individual errors on each separate measurement. So you have to keep in mind that whenever you are doing a summation, whenever you are adding two quantities and on each quantity you have an error, therefore the third quantity which you are forming, the error on it is going to be the addition of the individual errors. However, you have to keep in mind that that equation is actually specific for when you only have a summation, meaning it's not applicable to any other case. It's only applicable in the case where you have summation, when you are adding two individual measurements up. Moreover, that equation is also applicable to when you have subtraction. So if you have a summation or if you have a subtraction of values, the error on the final quantity that you have found is going to be the addition of the individual errors. So over here we can generalize that equation to be, let's say you have a certain quantity Q, which is found by adding a Q1 to Q2. Therefore, the error on Q is going to be the addition of the individual errors on Q1 and Q2. So delta Q would be equal to delta Q1 plus delta Q2. And that would be the first equation for the propagation of error, where the error on Q1 and the error on Q2, they added together in order to form an error on that third quantity which has been formed. And like I said before, that equation is going to be applicable to whether you have additions or differences. So even if you are actually subtracting two values from each other, that equation for the error is also going to be applicable, meaning that the error on the final answer that you have found is going to be the addition of the individual errors. You can consider the following example, which you can try at home for the differences. Let's consider that you have two containers that are filled with water, and you want to find simply the mass of the total water in both containers in addition to the uncertainty estimate on that mass of water. So let's say you have the mass of the first container, which consists of the container itself plus the mass of water inside, is equal to 540 grams plus minus a certain uncertainty estimate of 10 grams. And then you have the mass of the empty container, which is equal to, let's say, 72 plus minus a certain uncertainty estimate of 1 gram. And then you have the mass of the second container, which contains water, which is equal, let's say now, to 940 grams plus minus a certain uncertainty estimate of 20 grams. And finally, you have the mass of that empty container, of that second empty container, which is equal to, let's say, 97 plus minus 1 grams. So like I said, the target over here is actually to find the total amount of water in both containers and to find the uncertainty estimate of water. So let's say M total, or M water total, is actually equal to 540. So we have the mass of that first container plus water. So 540, you subtract to it the mass of the empty container, which is 72, plus the mass of that second container, which is 940, minus the mass of that second empty container, which is 97, and then you get a certain value for the mass of water. Now after getting a value for the mass of water, now we need to find delta M, which is none other but the uncertainty estimate on that total amount of water over here. How can we find it? You can find it by following the same approach which I have followed before. So over here what we have found, actually we have found the expected value of water. So that value that we have found is actually the expected value, or simply the best estimate. After doing so, after finding the expected value, now you are going to follow the same approach, meaning you are going to find M max, which is the overestimated value of water, and then you are going to find M minimum, which is the underestimated value of water, and you are going to find out that actually your expected value would be lying in the middle. And then the deviation that you have between these two is going to be none other but that margin of error. After doing so, you are going to check the validity of that equation, that for a difference over here, the error on the final answer that you have is going to be none other but the addition of these individual errors. But here you have to keep one thing in mind, that sometimes whatever value that you obtain for the error, you should either round it up or round it down in order to render that entire problem compatible, or in order to render the deviation that you have found compatible with that equation that we have established over here. For example, let's give you a certain random values for the error in order to show you how you might be rounding up or rounding down a certain value for the uncertainty estimate. Let's say, for example, you have delta M equal to 72 grams, and then you have found delta M by applying that equation over here to be around 68 grams. So delta M over here, it was actually deduced from the deviation between M expected and M max and M minimum, and delta M over here, let's say it was found by applying that equation. In that case, that value for delta M, it's going to be rounded up to 70 grams, which can be written as 7 times 10 grams, and that value over here, it can be rounded down to 70 grams, which can be written as 7 times 10 grams. And that is actually what I mean by rounding up or rounding down a certain value for the error in order to render that entire problem accurate or precise, or to render the deviation between M expected and M max and M minimum compatible with that equation for the individual errors over here. Now we are going to move on to another example in the propagation of error methods, and we are going to consider that we have a rectangular piece of wood which consists of a certain width and a certain height. And we are going to consider that the width and the height, they were actually measured in the lab. Therefore, we have an associated uncertainty estimates on each of the width and the height. So let's say the width is around 30 centimeters plus minus a certain uncertainty estimate of 0.3 centimeters, and then we have the height, which is equal to 20 centimeters plus minus 0.3 centimeters. Keeping in mind that these values are actually random, they are arbitrary. Now let's say the target is actually to find the area of that rectangular piece of wood in addition to finding the uncertainty estimate on that area. So we need to find the area and we need to find the uncertainty estimate on that area. In order to find the area, we are going to follow the same method as before, meaning we are going to find the expected value of the area, or the best estimate value of the area, which consists of multiplying the width times the height without factoring in each of these uncertainty estimates. So in that case, area expected, or simply the best estimate value for the area, is actually equal to the width times the height, which is equal to 30 times 20, which is equal to 600 centimeters squared, and that would be the best estimate value of the area. Now what we need to find is, we need to find delta A. How can we find delta A? To find that amount of uncertainty on the area, we are going to follow the same procedures that we have followed before, meaning we are going to be determining the overestimated value of the area by adding each individual error on the width and the height, and therefore multiply them and finding a max. And then we are going to find the underestimated value of the area, meaning we are going to be subtracting each individual error from the width and the height, and therefore we are going to find a minimum. So let's start by finding a max. A max is equal to W max times H max, which is equal to 30.3 centimeters, so 30 plus 0.3 times 20 plus 0.3, which is 20.3. So over here we have 30.3 times 20.3, which is equal to 615.09 centimeters squared. In a similar manner, we are going to find a minimum, which is equal to W minimum times H minimum, which is equal to now 30 minus 0.3, which is 29.7 centimeters, times 20 minus 0.3, which is 19.7 centimeters. So we have 29.7 times 19.7, which is equal to 585.09 centimeters squared. So over here we have three values. We have the expected value of the area, a max, and a minimum. So if we have a look at that value for the expected area, we can see that it's almost in between these two values, but not quite, simply because over here we actually have the decimal, the 09 decimal in each value. So if we cancel out the 09 in here and the 09 in there, actually the value of 600 would be halfway in between 615 and 585. Therefore, A expected is actually equal to 600 centimeters squared. Now, what would be the amount of uncertainty on A expected? As we can see, 600 is actually deviating by 15 centimeters squared from A max, and also deviating by 15 centimeters squared from A minimum. Therefore, delta A is actually equal to 15 centimeters squared. But now the question is actually how that uncertainty of 15 centimeters squared is determined from the individual uncertainties on the width and on the height. Meaning that how that 15 centimeters squared, it was actually determined from these two individual values of uncertainties on the width and the height. For instance, if we try the equation that we have established before for the addition or for the subtraction of individual values, which states that delta Q is equal to delta Q1 plus delta Q2, we can see that delta A, which is equal to 15 centimeters squared, is actually different than delta W plus delta height, which is equal to 0.3 plus 0.3, which is equal to 0.6 centimeters. So as we can see, that equation that we have established before, it does not hold in the case where you have a product. So it is only specific for the case where you have an addition or subtraction. Moreover, if we consider, let's say, delta A is equal to delta W times delta height. Delta W times delta height is none other but 0.3 times 0.3, which is equal to 0.09 centimeters squared, and delta A is equal to 15 centimeters squared. So also that equation is not applicable. Now what can we do in that case? For such a specific example, we are going to introduce a notion which is called the fractional uncertainties. So we are going to be introducing now a notion which is called the fractional uncertainties. Whether the fractional uncertainty in the area, or the fractional uncertainty in the width, or the fractional uncertainty in the height. So what do we mean by the fractional uncertainty? If we consider the uncertainty in the width, which is delta W, and we divide it by the width itself, therefore we have the following ratio, which consists of the amount of uncertainty in the width, which is 0.3, divided by the width itself, which is 30 centimeters, and that would give us a value of 0.01. And of course, that value is unitless, since we are dividing centimeter by centimeter. So that value of 0.01, it actually means that we know the width in the rectangle up to a precision of 1%. So that value over here is actually multiplied. So that value over here is actually multiplied by 100 in order to turn it into a percentage. So that value, it implies that the width of the rectangle is known up to a precision of 1%. And in that case, that ratio that we have written over here, which consists of the uncertainty over the width, delta W over the width, it is actually none other but the fractional uncertainty equation in the width. So whenever you divide the uncertainty estimate by the quantity, by the physical quantity on which you have that error, therefore you would be defining the so-called the fractional uncertainty. So in a similar manner, we are also going to be finding now the fractional uncertainty and the height, which is delta H over H, which is equal to 0.3 divided by 20, which is equal to, so we have 0.3 divided by 20, it's equal to 0.015. So that value over here, it actually implies that we know the height and the rectangle up to a precision of 1.5%. And in a similar manner, we are going to find the fractional uncertainty in the area, which is equal to 15 centimeters squared divided by 600, which is equal to now 15 divided by 600, it's equal to 0.025. So what can we deduce over here? Over here we have found the first fractional uncertainty in the width, which is equal to 0.01. Then we have found the second fractional uncertainty in the height, which is equal to 0.015, and we found a third fractional uncertainty in the area, which is equal to 0.025. And that value, it implies that we know the area of the rectangle up to a precision of 2.5%. So if we combine these first two uncertainties, if we add them up, we can clearly see that the fractional uncertainty in the area is actually equal to the fractional uncertainty in the width plus the fractional uncertainty in the height. Therefore, we can establish the following equation, that delta A over A is equal to delta W over W plus delta H over H. So we can deduce in that case that whenever we have a product, the fractional uncertainty and the quantity which has been formed by that product is equal to the addition of the individual fractional uncertainties on each measurement. And that equation, it also holds true for whenever you have a quotient, meaning if you have also a division, that equation is going to be applicable in that case. So you have to keep in mind that whenever you have a product or you have a division or a quotient, in that case, the fractional uncertainty on the third quantity which has been formed by that product is equal to the summation of the individual fractional uncertainties on each parameter of that product or division. Now regarding the division, I'm not going to prove it. You can try any example at home and you can try to prove it yourself, because it's going to be similar to that case, to the case of the product. You are going also to end up with delta A over A equal to the summation of the additional two fractional uncertainties on each individual value. So over here now we can actually generalize that example and replace the area and the width and h by a certain arbitrary physical quantity q. So in that case, delta q over q, meaning the fractional uncertainty in q, is actually equal to delta q1 over q1 plus delta q2 over q2. And of course, keeping in mind that this is only applicable in the case where, let's say, q is equal to q1 times q2, or q is equal to, let's say, q1 over q2. So it's only applicable in the case where you have a product or in the case where you have a division. Now, before we proceed to the next part, we are going to introduce a concept which is called the quadratic sum of uncertainties. So what is that concept and why do we need it in the first place? So we are going to be introducing the quadratic sum of uncertainties. In the previous two cases, we have established two different equations. We have established an equation for the error which states that the error on the third quantity which has been formed by a summation or by a subtraction is equal to the summation of the individual errors, delta q1 plus delta q2, and that would be for the sum or for a difference. And then we have established a second equation which states that the fractional uncertainty in the third quantity which has been formed by a product or by a division is equal to the sum of the individual fractional uncertainties. So delta q over q is equal to delta q1 over q1 plus delta q2 over q2, and that would be in the case of a product or a quotient. However, the calculated uncertainties by these two rules, they can be unnecessarily large or overestimated in a sense. So reducing these uncertainties, it would make sense. It would be the most realistic approach to do. But first off, let's have a look on why do we think that these uncertainties are actually unnecessarily large. Let's have a look at the first example that we have done previously, which consists of two cylindrical rods, and we joined these two rods in order to find a rod which consists of one entity. Then we have found the length of that rod and we found the estimate of uncertainty on that rod. However, over here we have found the best estimate value of the length, and after that we have found an overestimated value and the underestimated value. Keeping in mind that the overestimated value implies that we are actually adding each individual error to L1 and L2, and the underestimated value of the length implies that we are actually subtracting each individual error from L1 and L2. And then we have actually went with a case for L expected, which lies halfway between L max and L minimum. But when it came to the error on L expected, the error on L expected is actually overestimated, because over here what we are doing is actually we are adding each individual uncertainty to each other. We are adding the uncertainties up. Whereas over here for L expected it does not include any margin of error. So we have actually factored out delta L1 and delta L2 from the values of L1 and L2 in order to find L expected. Whereas the error on L expected is actually overestimated, meaning that it can be much larger than the expected error on that length L. So in that case, we are going to introduce a concept which is called the quadratic sum of uncertainties, which consists on squaring each individual error, delta L1 and delta L2, and then taking their square root. Because you have to keep in mind that when you have a very small value and you square it, therefore you are rendering that value even smaller. And then when you take that square root of that value, also you are rendering it much smaller. So in that case, delta Q would be equal to delta q1 squared plus delta q2 squared, and taking the square root of that entire equation. Therefore, you would be rendering the value of that error even smaller. And the same thing also should be applied on that equation for the fractional uncertainties, meaning that delta q over q is going to be equal to delta q1 squared over q1 squared plus delta q2 squared over q2 squared, and square root for that entire equation. Because you have to keep in mind that delta q, it was found on an expected value of q, from which we have actually factored out the individual uncertainties on q1 and q2. So in both cases, actually the errors, they might be overestimated and we need to reduce them. So to reduce these errors, we are going to be applying the quadratic sum of uncertainties. And the reason why I introduced that concept, because if you remember the general equation for the propagation of error, which consists of a series of partial derivatives, but each partial derivative is actually squared, and finally we have taken the square root of that entire equation. Therefore, later on, after we establish the general form of the propagation of error, we are also going to be applying the quadratic sum of uncertainties in order to render that equation much smaller, or in order to render the value of the error much smaller. Now moving on to the final part in our propagation of error topic. As you know, most mathematical operations, they aren't as simple as the ones that we have seen before. So the propagation of error equations that we have established previously, whether for the addition or for the difference or for the product or for the quotient, they cannot be applicable to complicated mathematical operations such as the square root or the cosines or the sines or any operation that involve complexities. So let's consider that you have a certain function y equal to square root of x. So over here we have a function of one variable. And let's consider a certain expected value for x, which we are going to call it the best estimate of x, or the expected value of x, which has an associated uncertainty on it. So we have a certain value of x, which is x best, and a certain associated uncertainty on it, delta x. And let's say that we want to find the corresponding expected value of y along with its associated uncertainty, delta y. So for that x best, we want to find the corresponding y expected value plus the amount of uncertainty on that y expected. How can we do so in that case? A simple way to approach this problem would be to draw a graph of the function y equals square root of x. So we are going to consider the following xy plane, in which we are going to be drawing the function y equal to square root of x. And then over here we have a certain value for x best. We are going to choose it in an arbitrary manner on that x-axis. So over here, let's say we have x best. But on x best, we also have a certain margin of uncertainty. So x best, it can vary within x best plus delta x or x best minus delta x. So let's say over here that we have a certain placement for x max, and x max in that case it consists of x best plus delta x. And over here, let's say we are going to be placing x minimum, which consists of x best minus delta x. So that value of x best is actually varying between two values, x max, which consists of x best plus delta x, and x minimum, which consists of x best minus delta x. Now let's take the extrapolation of x best toward that curve, and then from that point of intersection we are going to extrapolate toward the y-axis in order to define over here so-called y expected value, which corresponds to x best. So by taking that extrapolation toward the curve, and then by taking another extrapolation from that point of intersection toward the y-axis, we are going to be defining y expected. In a similar manner, by taking two extrapolations from x max and x minimum toward the curve, and then from the points of intersections we are going to take other extrapolations toward the y-axis, we are going to be defining over here from one side y max, and from the other side we are going to be defining y minimum. Keeping in mind that that gap over here, it corresponds to none other but the margin of uncertainty delta x, and in a similar manner, these two gaps over here, they correspond to the margin of uncertainty, which is delta y. So these three values, they are actually equally separated. So the separation between y expected and y max is none other but delta y, and the separation between y expected and y minimum is none other but delta x, and in a similar manner over here. Now, let's say that we want actually to find the expected value for y. So we know that the function is given as y equal to square root of x. And we already have, let's say, a value for x best. So you replace in that equation x by x best, and therefore you would be finding the expected value of y. Now, how can we find the error on y? How can we find delta y in that case? So we said earlier that we have over here a function of one variable. We have y equal to f of x, which is equal to square root of x. So what would happen if we take the first derivative of that function with respect to x? So let's say we are finding y prime, which is equal to the derivative of y with respect to x, which is equal to f prime of x. What do you think the first derivative of a function actually implies? The first derivative of any function, it implies that we are finding the slope of the tangent line to that function at a certain point x. So that derivative over here, that first derivative, it implies that we are actually finding the slope of the tangent line to fx at point x. However, that slope to the tangent line is going to be found at a certain specific value. It's not a random value of x, but rather it's at value x best. So it's going to be at that value over here. And what would be the tangent line in that case? The tangent line in that case is going to be a straight line, which is going to be tangent to that curve, but at point x best. So over here we have already taken the extrapolation from x best toward that curve. So over here we know that point of intersection. So we are going to be drawing the tangent line to that curve at point x best over here. So we are going to start by drawing the tangent line to that curve at point x best. So like I said before, the first derivative of any function is going to correspond to the slope. Slope of what? Slope of the tangent line to that curve at point x. But in our case, that point x was actually specified to be x best. Now let's consider the following right triangle. So over here we have that small segment which consists delta x. So that horizontal segment over here, it consists delta x. And then over here we have that vertical small portion which is going to consist delta y. And then over here we have that small portion of a straight line which is none other but the third segment of that right triangle. So let's try and enlarge it. So over here, first off, we have a horizontal portion which corresponds to delta x, and then we have an upright portion which corresponds to delta y, and then we have that third portion, that third segment, which is going to correspond actually to that tangent line or to part of that curve over here. And as we can see, it is actually a straight line. Now what we need to do next is actually we need to find an expression for that straight line in terms of delta y and in terms of delta x. We know already that for a straight line we have a general equation which is y equal to ax. So any straight line, it can be actually represented by an equation of the form y equal to ax, where a would be the slope of that straight line. But in our case over here we have defined the slope to be the first derivative of a function with respect to x. So that slope over here, that equation of slope, we can replace it by dy over dx. Therefore the equation becomes y equal to dy over dx multiplied by x. But as I have said previously, what we want to find is we want to find an expression for that segment in terms of delta y and in terms of delta x. But over here we have an equation for y equal to dy over dx multiplied by x. Now, since over here we are actually dealing with very small uncertainties, we are dealing with a segment which is represented by delta y, which is a very small amount of uncertainty, and we are dealing with a segment which is represented by delta x, which is also a very small uncertainty. Therefore, a fundamental approximation of calculus would enable us to replace y by delta y and x by delta x. And therefore, the expression becomes delta y equal to dy over dx multiplied by delta x. And therefore, we are actually expressing the uncertainty in y in terms of the slope, which is none other but the partial derivative of x of y with respect to x, multiplied by the uncertainty in x. So to repeat myself. So over here actually we had a certain curve, which is none other but the function y equals square root of x. And we had a value of x best for which we wanted to determine the corresponding y expected value, which can be easily determined, but moreover we wanted also to find the error on y expected. So we wanted to find delta y, that delta y. So over here, first off, we considered the first derivative of the function that we have, dy over dx. But by considering the first derivative of a function, meaning that we are actually considering the slope of the tangent line on that function at a certain point x. And that point in our case, it was actually specified to be x best. And then we draw the tangent line over here to that curve, so on and so forth, at point x best. Then we have considered the following right triangle, which consists of delta x, one segment is delta x, another segment is actually delta y, and then we had that unknown portion that we wanted to express in terms of delta y and delta x. But we know that that portion is actually a straight line, so by going back to the equation of a straight line, y equal to ax, we started from that starting point, and then we moved on forward. A over here represents the slope, and the slope it was defined to be the first derivative of the function that we have, dy over dx. So we replaced it by dy over dx, and we had y equal dy over dx multiplied by x. But the aim it was what? The aim it was to find the error on y expected. So we needed to find a way in order to move from that expression to that expression. So since over here the segments were expressed in terms of dy and dx, and since dy and dx, they are very small quantities, meaning that they are increments that they cannot be seen in the naked eye. Therefore, in that case, by going back to a fundamental approximation of calculus, we were able actually to replace y by delta y and x by delta x. But otherwise, if you have very significant changes in y and x, therefore, we always have to stick to that equation, and therefore we are not dealing with errors anymore. We are not dealing with a small amount of uncertainties anymore. However, since we had over here small uncertainties, we were able actually to apply a fundamental approximation of calculus in order to move from that expression to this one over here. And therefore we have expressed the error on y in terms of the partial derivative of y with respect to x, and in terms of the error on x. But keep in mind that that equation over here is going to be an equation applied in the case where you have a function of one variable. So that equation is for a function of one variable. So over here we have y equal to square root of x. So let's try and find delta, or the expression for of delta y for y equal to square root of x. So delta y would be equal to derivative of square root of x with respect to x multiplied by delta x, and the derivative of the square root of x in that case would be half times 1 over square root of x multiplied by delta x. So that would be the expression, the final expression for the error on y for the function y equal to square root of x, and like I said, that would be very specific for a function of one variable. Now what if we have a function of two variables? So let's say now we have q of x and y. So we have a function of two variables, and on x we have a certain amount of uncertainty, and on y we have a certain amount of uncertainty delta y, and we want to find the error on q. Therefore, by following the same logic, we are going to start with that expression over here, but we are going to carry on by adding another term which is going to correspond to the partial derivative of the main function with respect to its second variable y multiplied by the error on y. So the expression becomes delta q equal to dq over dx multiplied by the error on x plus dq over dy multiplied by the error on y. And that would be the expression for two variables. Now what if we have n number of variables? So we have a function of x, y, z, so on, etc. Therefore the expression becomes delta q equal to dq over dx delta x plus dq over dy delta y plus 3 points dq over whatever d beta times the error on beta, so on, without adding the square root. Later on we are going to talk about the square root. So that would be the final expression if you have n number of variables. So you are going to keep following the same pattern that we have followed before by adding each time a partial derivative of the main function with respect to its variable multiplied by the error on that variable. Now that would be the final expression for the propagation of error, which is going to be unifying for all special cases that we have seen before. So in that case, you are no longer in need to apply the equations for the special cases that we have defined before, but rather that equation is going to be unifying for all special cases involving the propagation of error. Now there is still one thing that we need to talk about, which is the quadratic sum of uncertainties. So before we have introduced the notion or the concept of quadratic sum of uncertainties, which we said that it helps us to lower the overestimation of an error on a physical quantity. So as we have said before, that sometimes the error, they can be unnecessarily large and we need to reduce them. And in order to reduce them, you actually resort to a method which is called the quadratic sum of uncertainties, which consists of squaring each term of the equation and then taking the square root of that entire equation. So by applying the quadratic sum of uncertainties to that general equation of propagation of error, we can find out that delta q is equal to dq over dx times delta x squared plus dq over dy plus the error on y squared plus dq over dz plus the error on z squared, so on and so forth, and then you take the square root of that entire equation, and therefore you would be actually reducing the estimate of uncertainty on a physical quantity. And over here you have to keep in mind that whenever you are finding an error, basically you are not finding an exact and precise value. So over here you might be conflicting between which equation you want to apply. Actually both equations, they are correct, they are acceptable, and in some textbooks they actually apply that version of the equation. But in our lab we are going to be sticking to the equation which actually uses the quadratic sum of uncertainty as a way in order to reduce any unnecessarily large measurement of error on a physical quantity. So we are going to be sticking to that equation over here. Moreover, in the manual that I have sent you, they don't actually use delta, they use alpha. But they are basically the same. Delta and alpha, they basically mean the same. They are both a measure of uncertainty, a measure of error. So instead of having delta q over here, we are going to have alpha q equal to dq over dx multiplied by the error on x squared plus dq over dy multiplied by the error on y squared plus dq over dz multiplied by the error on z squared, so on and so forth if you have many other number of variables. And that would be the final expression for the propagation of error, which is, like I said before, it's an equation that unifies all special cases that we have seen before. So whether you have a summation, whether you have subtraction, you have a quotient, you have a product, you have cosine, you have a sine, you have a logarithm, you are going to be applying that equation in order to find the error on the physical quantity. Now let's consider an example that you are going to be solving at home. So let's consider that we have a rectangular block. you have the following rectangular block which has a certain mass, let's say 10 kilograms plus minus 0.5 kilograms and an amount of uncertainty on it of 0.5 kilograms. It has a certain length of, let's say, 80 centimeters plus minus 0.21 centimeters. It has a certain width of 40 centimeters plus minus 0.5 centimeters and a certain height of 20 centimeters plus minus 0.6 centimeters. And let's say that you want to determine the density of that block, of that rectangular block, and you want to determine the error on the density. So over here you have all of these parameters. We know that the density is given as mass over volume. You are going to proceed from here in order to find the value for the density. After finding value for the density, of course, along with the unit, and the unit, it has to be in SI units. So over here you have units in centimeters. You have to convert them to meters, whether for the main unit, whether for the main value or for the error. So each one will be multiplied by 10 to the negative 2. Then after finding the density, now you are going to be applying that equation over here in order to find the error on that density. So over here we have 1, 2, 3, 4 variables. So over here we have a function of the mass, the length, the width, and the height. We have a function of 4 variables, meaning that we are going to have 4 terms for the propagation of error equation. So we are going to be deriving rho 4 times with respect to each one of its variables. But here you have to keep in mind one thing, that let's say you are deriving del rho with respect to the mass. So you are doing the first derivative with respect to mass. In that case, when you are deriving with respect to mass, the other quantities are going to be held constant. They are not going to be varying. And in a similar manner, when you are deriving with respect to the length, the mass, the width, and the height would be held constant. And when you are deriving with respect to the width, the mass, the length, and the height would be considered a constant, so on and so forth. What do I mean by being held constant? Let's consider the example that we have done previously. The area equal to the width times the height. Let's say that we have an error on both of the width and the height, and we want to find the error on the area. Therefore, the error on the area would be what? Would be derivative of the area with respect to the width times the error on the width squared, plus derivative of the area with respect to the height times the error on the height squared. Square root for that entire equation. Starting with the first derivative. We are deriving the area with respect to W, therefore h would be held constant. Therefore, the derivative of WH with respect to W would yield h times the error on W squared. Plus, now we are deriving the area with respect to h. So now W would be held constant. So therefore, that would yield W times the error on h squared. And that would be the final expression. Then you replace the values and you get a value for the error on the area. And the same principle, you have to apply it over here. So you have a function of 4 variables, you have to do 4 derivations, and then you have the values. You are going to plug them in here, but you have to keep in mind that the units, they are not in SI units. You have to do that conversion before. And that would be it for the propagation of error part.